Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the module 10, which will cover the topics such as earthquake geodesy. And in the lecture 1 today, we are going to cover the concepts such as measuring the ground motions, global positioning system, that is one of the way of measuring the deformations on the ground. Within the global positioning system, we will talk about precision and limitation, and then how the data is collected using global positioning system. We will briefly talk about it. Thereafter, we will be talking about a advanced technique, that is synthetic aperture radar interferometry, where we will be talking about its advantages and the limitations. Finally, we will be having the summary of today's lecture. Let's start with the lecture. As you know, the earthquake, whenever it occurs at any place on the globe, then it always accompanied with a large amount of deformation. And that deformation is the main cause of release of high amount of energy in the form of seismic waves. When it occurs, it brings lot of devastation to the area and also to the life, property, etc. So in order to understand the complex phenomena of the earthquake, we also need to understand how deformation at the time of the main shock is occurring, how it is accumulated prior to the happening of the main shock. So what kind of deformations happens in the pre-seismic stage and also the inter-seismic stage, and after the earthquake what happens. So that we can study by using the information about the deformation or the locations of the points on the surface that are just before the main shock, how they are moving with respect to the plate motion. So it is very important or essential to study about those complex deformations that are taking place before the rapid deformation during an earthquake. And those complex deformations that are relatively slow and on a very broad region, we need to understand by using the concepts in geodesy. So this will provide you the additional information about earthquakes and the processes that are causing them, and can be obtained by measuring slow ground deformation using techniques in geodesy. And geodesy is basically the science of the earth's shape, and there are many techniques that can be used in the geodesy to find out the relative motion in real time of the geodetic monuments, which are basically the markers in the ground. And for the markers, we generally use the metal discs that are attached to the rocks that are often seen at the mountains peaks, and they have various kind of designs and also used in the hope of minimizing the effect of the soil or the near surface deformation or the motion that masks the tectonic movement. So near surface, due to the soil erosion and other phenomena takes place, and that can also affect the data collection that we want to have in order to find out the motion. So in soft sediment, like the monuments that we are making for the recording are often like the steel rods that we generally penetrate and arrange it into the very deep earth. And the popular term for the monument is benchmark, and geodesists traditionally reserve this term for monuments used to study vertical motions. And there have been the many new techniques have arisen that in the geodetic methods that also uses the signals from the space that basically allow us to use the three components of the positions so that we can have measurement up to sub-centimeter precision. So as a result, the geodetic data before and after the earthquakes are now given the co-seismic motion to high precision so that we can have much more easier way so that we can find out the deformation that is happening prior and after the earthquake. Three of these techniques are used to locate geodetic markers. One is the very long baseline interferometry, which basically uses the differences in the time when the radio signals from distant quasars arrive at different points on the surface. There is another technique that is satellite laser ranging. In short, it is known as SLR, that uses the time required by the light from ground-based lasers to bounce off satellites. And the most popular technique nowadays today is the global positioning system. In short, it is known as GPS, and that relies on the travel time of the radio signals between satellites and the ground stations. If we talk about the global positioning systems, those are developed in 1970s and it is very popular for most tectonic applications. And for a single GPS receiver, you need minimum of 4 satellites that they can determine position to a precision of 5 to 100 meters. And GPS can be used for real-time monitoring and the navigation system. And if you want improvement to centimeter or better precision, it can also be achieved by using the phase delays of the microwave carriers. So if you look at this diagram, this is the constellation of the GPS satellites. So when we start to have GPS system, which was basically open for the public use by US, and it was open in 1996. Before that, from starting of the 1974, US military has used it, and thereafter it has become open for the public use. And in this system, you at least need a collection of 4 satellites for a GPS receiver that is on the surface of the earth. It receives signals from the satellites to identify its coordinate in the form of 3 coordinate system, 2 horizontal and 1 vertical. And if you look at this picture, you can see at a time, if suppose this GPS is there, it is also recording the data from 4 satellites, and likewise this is also there, this is also recording the data from 4 satellites that is used for relative positioning. And the solid arrow is indicating towards the baseline vector to be measured. If we talk about the precision of the global positioning system, the carrier frequencies are larger than modulation, so their phase provide precise positions, and the use of the differential signals from multiple satellites recorded at multiple receivers reduces the clock error. So we have atomic clocks that can basically find out the correct timing of the delays of the signals that are being received by the receivers on the surface. So GPS studies can achieve positions better than maybe less than 10 millimeters. There are 2 modes of GPS data collection. One is the survey mode, another is the continuous mode. So this is just a pictorial view of mode of data collection. One, as I told you, is the survey mode, in which you have GPS antenna set up for a period of time at a place, and then you just take it out, and after some time you may revisit the place. But in case of second mode of global positioning data system, where we collect the data in the continuous mode, the GPS receivers are installed permanently. So in this case, the data is quite better. It is more precise, and but it is at the cost of higher amount of money involved. So the continuous mode certainly is better in terms of the precision, but it involves like higher amount of cost. But in case of survey mode, it doesn't involve much cost, but the precision is basically you are going to compromise. So global positioning system has some limitation. So when you are putting your geodetic marker at a place, you need to make sure that in case of earthquake geodesy, your marker should be near to the anticipated earthquake, and which is not always possible. So we need to make effort, and resources are required to install survey monument in advance in hopes that an earthquake will occur nearby. So that can be done in the active areas where the earthquakes are very frequent. That can be done in order to find out the accurate positions, but that is not almost always position. If suppose there is an area which is relatively aseismic in nature, then when you are placing your GPS, then it may not give you that precision. So this issue can be overcome by the use of synthetic aperture radar interferometry. In short, it is known as INSAR, and that is a way to escape this issue that was offered by GPS and is provided by synthetic aperture radar interferometry from satellites. So it basically facilitates high resolution radar mapping from spacecraft or aircraft, and in this INSAR we are going to use the single slit diffraction concept, and it is used to estimating the resolution of a physical radar. So the resolution, that is theta d, is equal to lambda by d, which is further equal to x by r. Radar's antenna's length is represented by small d, lambda is the wavelength, x is the resolving size of the object on the surface of the earth, and r is the altitude. So if you look at this particular diagram, you can see this is the size of the object x, and r is the altitude, and theta is the angle at the antenna. So because the radar wavelength are tens of centimeters, a radar antenna a few meters long orbited hundreds of kilometers above the earth can normally resolve topography only on a scale of kilometers. So for this you can use a moving satellite to simulate an antenna much larger than the satellite's real antenna. For example, if you are using the 10-meter antenna, then it can basically assume as a 4-kilometer synthetic antenna. The synthetic antenna can thus resolve both topography and the crustal deformation on a footprint of tens of meters. So it will basically improve your resolution from kilometers to basically tens of meters. The phase difference between radar signals with wavelength lambda reflected from the Earth's surface and recorded by antennas at position A1 and A2 can be given by this particular formula, where phi is equal to 4 pi by lambda R2 minus R1. So R2 and R1 basically the range from the antenna at AI to the reflection point. The antenna baseline separator vector B. So if you look at this particular diagram, this is the baseline vector B, and satellite flight H are known from the satellite orbit. So these two parameters we already know, H and the B vector, baseline vector, separation vector, and because the baseline length B is much shorter than the ranges Ri, an analysis like that used to derive the earthquake rupture time shows that the elevation of the reflecting point is H minus R1 cos theta. You can just do the small trigonometry to find out this particular value. So topography can be mapped from the space, and this method is called interferometry, which is used for both Earth and the planetary mapping, such as the Magellan mission to Venus. And two such radar images can detect ground motion between successive measurement, and if suppose if differences in the satellite position between the measurements are removed, a vector surface displacement d causes a phase change, where delta r is the projection of the vector displacement and along the look direction connecting the satellite and the reflection point. To find the full displacement vector, observations from ascending, that is moving north, and descending, moving south, tracks of the satellite or different satellite can be combined. The results are shown as a phase difference map called differential interferogram, and this is one of the image. So this is the image of the phase difference, that is from 1992 Landers having the magnitude of moment magnitude 7.3, and from the Big Bear earthquake in Mojave Desert of Southern California. You can see a range change delta r of lambda by 2 cause a phase change of 2 pi that appears as a one fringe full shading change in the map. So you can see the difference between the two. In this map, the C-band radar has a frequency of 5.2 gigahertz, and so a fringe corresponds to 28 millimeter of motion. The observed fringe pattern is coherent over large areas where deformation is resolved. The pattern is reasonably similar to a synthetic interferogram generated for a detailed model of the Landers rupture, which involved several meters of right lateral strike slip on a complex set of northwest striking faults extending from about 85 meters. So this is the image for SAR interferogram data and modeling for 1982 Landers and Big Bear earthquakes that happened in 1992 in the Mojave Desert of Southern California. What are its advantages? Although radar images before an earthquake are needed, satellite can acquire them over areas far too large for geodetic monument to have been installed everywhere. INSAR maps deformation on a space of tens of meters far denser is practical with geodetic monuments. INSAR is especially sensitive to vertical motions because in GPS you need 4 satellite and it gives the vertical position, but it is not that accurate. But in case of INSAR, it is especially sensitive to vertical motions, the component of which the GPS is the least precise. It recovers motions only in the look direction. It cannot be, so these are the limitations that we are talking about now. So it recovers motion only in the look direction. It cannot be used in some areas of steep topography where the radar beam cannot penetrate or where the slope facing the radar is so steep that several points have the same range to the radar. Another limitation is that non-tectonic changes between images such as those due to the vegetation growth or weather conditions can mask the effect of the crustal motion. INSAR provides relative changes within an image that is tens to hundreds kilometers across but does not provide absolute positions on a plate-wide or global scale. Some more limitations. This poses no problems for individual earthquake studies but means that it alone cannot be used for large-scale applications like plate boundary studies. The advent of space-based methods like GPS, INSAR, which makes collecting geodetic data faster and easier, have made earthquake geodesy and seismic wave studies common overlapping approaches to earthquake studies. Hence, although seismology and the earthquake geodesy were long viewed as very distinct owing to their different instrumentation, earthquake geodesy is increasingly viewed as very low frequency seismology or earthquake seismology as high frequency geodesy. So this is the summary of today's lecture. Geodetic methods using signals from space permits all three components of positions to be measured to sub-centimeter precision and now give co-seismic motion to high precision much more easily than was previously possible. Very long baseline interferometry, satellite laser ranging, global positioning system are popular geodetic techniques to measure ground deformation. GPS uses a constellation of satellites transmit coded timing signals on a pair of microwave carrier frequencies synchronized to very precise onboard atomic clocks, so that we do not have much error in the data. GPS data can be obtained for continuous period of time or short period of time. So there are two modes of survey, the survey mode, and there is another continuous mode. So in the continuous mode it is much more precision is there. So the later one is much more cheaper. The short time period of survey is the very cheaper. The biggest limitation of geodetic data for earthquake studies is that the positions of geodetic mapper before the earthquakes are needed. So these positions are needed maybe in the nearby areas where the earthquake may be anticipated, but you can use like the areas where the earthquakes are very frequent, whereas seismic activity is very frequent, but it is not always true for the aseismic region where maybe in future some big earthquake may occur. For radar, D is the antenna length. So a radar a distance r above the earth's surface could resolve object of size x, where theta d is equal to lambda by d x upon r. X is the size of the object, r is the altitude, the d is the antenna length, lambda is the wavelength. The phase difference between radar signals with wavelength lambda reflected from the earth's surface and recorded by antennas at position A1 and A2 is this, where phi is equal to 4 pi by lambda r2 minus r1, and r is the range from antenna at A to reflection point. If differences in satellite positions between the measurements are removed, a vector surface displacement d causes a phase change. So phi is equal to will become 4 pi by lambda delta r, because r2 minus r1 will be replaced by del r, and del r will be d dot r cap, where del r is the projection of the vector displacement along the look direction connecting the satellite and the reflection point. The results are shown as phase difference map called as the differential interferogram. So this is all for today's lecture, and these are the references. Now we will meet for lecture 2 of module 10. Thank you so much. Bye bye.